Welcome to another session of electrical fundamentals. Today we are going to talk about our last component in DC, which is inductors. Now this inductor is a very interesting component, but before we dive in, let's talk about the symbol and the unit of measure. Okay, the symbol to represent inductor is L. Okay, just like C for capacitor, R for resistor, for inductors we use L. And it is measured in Henry, which is shortened as H, and often you will see it in millihenry of unit. Okay, before we connect any of the inductors in the circuit, let's talk about how these inductors are made, or what's even an inductance, and what affects it, and its characteristics and properties. Okay, so what is inductance? I have two definitions for it, and they are pretty similar. Okay, so first definition is a unit of measure. Measuring what? It's measuring how much energy it can store in an electromagnetic field. If you compare that with a capacitor, it was also a unit of measure as to how much energy that it can store in an electrostatic field. It was a static energy because we had two plates together, but this time we are storing the energy inside the magnetic field. So where is magnetic field came from? Well, back in the day, the scientists have observed that when you run a current through a conductor, which is essentially a wire, then it generates the magnetic field. Now the rate, as soon as you increase or decrease, whenever there was a change in current flow, either more or less, depending on how fast we make that change, that magnetic field was also changing at the same time. What it was more interesting is that as these magnetic field was generating and changing its size, every time it did that, by varying the rate of current change, it also created this voltage at the same time, as soon as the magnetic field was changing, but in an opposite direction from initial force. Okay, so if the current was flowing from left to right, because that's what the voltage direction, current direction is, that would generate a magnetic field. But as soon as a magnetic field was generated, it created a voltage, but it was sending it in the opposite direction. Why is that? The nature doesn't like the change. It wants to oppose the change. Okay, so by having that current inside, as soon as the magnetic field is generated, it actually forces, by creating the voltage, and pushes that current back. That is another definition of inductance. It is the property of electrical conductor who wants to oppose the change in current flow by creating these voltages, okay, in the opposite direction. And that voltage, we call it a back EMF, or back voltage, or counter EMF, or counter voltage. So we will talk more about why that's so important, but let's talk about how the inductance can be affected. Remember I said the inductance was a unit of measure as to how much energy that it can store in the magnetic field. So remember how we were just sending a current through a single wire, correct? And the magnetic field was generated. But what if we were able to put it in a loop instead of a single flat wire? And you will have the magnetic field generated in this direction, okay, depending on how the current was flowing, okay? But what if we actually coiled in this manner and sending the current through that way? Now, all of these wire coil, it's going to have its own, let's use the other pen, okay, it's going to have its own magnetic field. Okay, all of these will have magnetic field. And when those magnetic field when they came together, it amplified because you have this magnetic field and that magnetic field. When they came together, it amplified, just like ripples. Okay, so we were able to observe by creating the coil creating the wire in this coil format, the magnetic field was becoming a lot bigger, intensified, okay, and definitely stronger than sending a current through a straight wire. So oftentimes, because the inductor is made in this manner, you will see a symbol for inductor in the schematic diagram, the wiring diagram, as this. That represents a coil. Essentially, to have our proper inductance, it has to be in a coil format, because otherwise it will be pretty much useless. Now you will see this, or you may see this, which is one of the most popular, and you may also see this. Okay? So what are the difference between those three? Well, let's talk about this. One of the things that it affects, well, some of the things that affects the inductance, ability to store the energy, is, like we said, how about a Moore loop? So number one, number of turns. What am I talking about? If I have more turns per area, right? If I wrapped more coil, more wire, I will have more inductance, because it's just going to create that much more magnetic field individually in the wrapping. Therefore, my total magnetic field is going to grow, more room, more energy that it can store. Okay, the second one is what you see on the right. The scientists also observe that, see how the bottom one has nothing inside, nothing is actually wrapped around. Okay, it's air inside. However, if they use a core to wrap these, if they use the core and they wrapped around the core using this wire, this is a symbol for an iron core, and this is a ferrite core. If they use anything that is a permeable metal, they observed that the magnetic field was more concentrated, and it definitely became stronger. The stronger magnetic field, it was able to store more energy, therefore higher inductance. So core, type, and material. Number three, cross-sectional area of coil. If I was to cut this coil in half, top and bottom, how much do I have? More cross-sectional area, then I'm definitely going to have more inductance. Number four, a length of coil. You would think that longer coil will have a better, higher inductance. Actually, it's not. A shorter but more tightly packed. Okay, more tightly packed. So I rather use 1 inch and then just wrap over and over and over and over again. If I have a same length of, let's say I have 100 feet of wire, instead of the distance between here to here over a 6 feet, I'm just loosely wrapping it. Okay, I don't have that much cross-sectional area because there's some empty spaces in between. But if I just, you know what, the 100 feet, I'm going to pack all that wire into an inch space. I'm just putting it on top of each other, just winding it on top of each other. What that does is just really, really packs it, and it makes it a lot stronger. Therefore, you'll see these inductors, very, very thick in design because they're just not loosely wrapped in a long span of distance, but are very, very tightly packed in a short distance. So short, tightly packed will increase the inductance. So these are the 4 things that will affect the inductance of an inductor. Now, I've mentioned briefly about the back EMF, back voltage, or counter EMF, counter voltage, but I want to use a analogy to describe it even further. So inductors are like teenagers. It doesn't want to be disturbed. You know how the teenagers, when you wake them up in the morning, then they will resist getting up, but eventually they will give up and get up and go to school or go to their work. And at nighttime, this time, when they tell you to go to bed, well, they don't want to go to. They resist first, but eventually late at night they go to bed. So inductors are like that in nature. Matter of fact, the nature wants to resist any kind of change. Another analogy that I want to use for inductor is by having a water wheel. Okay, so what you have in front of is the water pump, which pumps as soon as I turn the pump on, and it's going to pump the water in this direction. Now we have one side a restrictor, and this represents the resistor. Okay, and we have this very, very heavy 10-ton water wheel. Okay, so let's turn on and see what happens. As soon as the water goes, and it's going to go this way, and it's going to go this way. However, which path do you think is more easy or easier for water to flow? Is it number 1 through the water wheel, or number 2 through the restrictor? Well, that water wheel is very, very heavy. So yeah, so some water is going to be there, but it requires a lot of energy. So the water wheel is actually not going to turn. It's going to start to turn, but at a very slow rate. So most of the time, the water is going to flow through this restrictor, even though it is restricted to a certain amount. Okay, so you're not actually going to see that much water come out on the other side of the water wheel. But eventually, the waters are still, at the entrance of the water wheel. Start to push a little bit in here and there, and the water will start to slowly but surely, it's going to start to move. As it starts to move, it's going to pick up its momentum, it's going to pick up its kinetic energy, and it will start to turn fully. Okay, and next thing you know, is it's already spinning at its maximum speed, passing the water down without any problem. Do you see that? When that happens, it already has its full momentum, and it requires very little energy, very little flow to keep that water wheel from turning. Okay? And in the beginning, it resisted current that's coming in. No, I'm heavy, I'm not going to let you flow, but over time it loses and it starts to turn, and it will not this time want to stop. When that happens, what do you think it's going to happen to the flow of the water? Do you think you'll see much water that's flowing through the restrictor? I don't think so, because this water wheel itself now is bringing, or is sucking the water out from the pump and directing most of the water flow through this water wheel. So you actually see very little water going through this restrictor now. Okay, so let's say it's at its maximum speed, and you know what? We had enough. Let's turn the pump off. When you turn the pump off, the water stops flowing. What do you think is happening to the water wheel? Is it going to, remember, this is really heavy and it's spinning really, really fast. And all of a sudden, when you turn the pump off, do you think that water wheel is going to and not flow, not turn again? No, it's going to continue to turn because it already has its momentum. It built up its kinetic energy and needs to release it, right? And eventually the friction will catch up and it will slow down. But again, when I tell you to stop the pump, it was still turning, correct? So it was resisting the change. That's the analogy of the inductor. Okay? In the beginning, when you turn the switch on, the current it's getting to the inductor, but then it's opposing with the full force. If this was a circuit, with an inductor and a resistor, okay, current is going to flow this way and that way. Even though it's restricted, it is much easier than flowing through the inductor because it's pushing back its full force. So when this is a 10 volts of a pressure that is sending the current down, it's going to stop it, oppose and resist by creating a 10 volts of energy in the opposite direction. It will never create more than the supply pressure. Okay, if I'm pushing with the 10 volts, then the back voltage will also be creating that much energy to push back the current flow. But eventually, they give up. Eventually, they give up, and then this back voltage is going to decrease, okay, and allowing the current to flow. As the current flow, the magnetic field is slowly being generated and storing all that energy, okay? Let's put a switch in here, and let's say I opened it up, okay? Let's say I opened it up and see what happens. Now, the current all of a sudden was flowing this way, now it stops. But what about the inductor? Is he happy about the change? No, just like the water wheel, it was still turning and drawing the water from the pump. So it wants to continue. The current was flowing through me. Why do you stop now? So what happens is it collapses the magnetic field. As soon as the current stops flowing through those coils, what happens is that very quickly that coil collapses. Okay? Sorry, not the coil collapses, the magnetic field collapses, and then within that magnetic field, all the stored energy is being converted into a electrical voltage, electrical energy, which is voltage, and sending it in the direction that the current was originally flowing in this direction. Even though I said stop, I'm not sending any more current down, inductors say, I have all these energy that I've saved up, well, and I'm going to collapse my magnetic field, all the energy, I'm going to convert that into a voltage, a back voltage again, and push it in the same direction that you were originally sending it down, okay? So that's what happens, and I just described a Lenz's law. Lenz's law pretty much describes the direction. It wants to oppose a change, and it will always create a back voltage in a direction opposite to your supply voltage, okay, your initial current. So how long does it take to charge the energy inside the magnetic field? Just like capacitor, it also has a time constant, and time constant was represented as tau and measured in seconds. Unlike our capacitor, which was for the time constant, it was a resistor times constant. For inductor, it's inductance over resistance. Yep, we have the fractions again, but that's how the formula goes. And what do you think? The time it takes to charge these energy, yes, it's a 5-time constant. Same as at discharging, it will take 5 tau, 5-time constant to deplete these energy, okay? So the graph is, we've already looked at the calculations for the capacitor, and it's exactly the same. But this time, it is actually storing the current. It's not the voltage that is charging, but it's the current. Okay? So let's take a look. We have a graph. In the beginning, is there any current that's flowing to the inductor? No, it's not. So we are looking at the inductor right now and to see how the current is doing. and current is nothing. It's not going through it. However, as the time passes, finally it's starting to give in. Okay, current, you can start to flow now, and to the point like the water wheel, it gains its maximum momentum, maximum speed, all the current is flowing. And that takes, okay, 5 time constant, right? And now, how much current does it charge it to? Imagine if it was 10 amps. Does it charge up to 10 amps? No, it never. Right? It never charges to that, but it's very, very close. After the 5 time constant, it is 99.3% of current that it charges. Okay? However, for the voltage is different. Let's take a look. For the voltage, let's look at the inductor again. When you first close the switch and the power supply or the battery is applying the power, the voltage, what happened? It instantly created a maximum voltage, a matching voltage to a battery, a power source, didn't it? And finally, it was giving up, allowing more current to flow, and back to nothing. So it will look like this for the voltage. Okay, it was matching same amount of force, same amount of voltage to push back. Okay, the created back voltage, but eventually it let go, allowing the current to flow, and finally current was flowing through the maximum, and then the voltage, there was no voltage left. Again, this is not a 0 voltage, but it's equivalent to 0.7% of the supply voltage. Okay, so if you compare that with a capacitor, it's backwards, it's opposite, correct? So let's clear this up and talk about our relationship between the capacitor and an inductor in the graph. Here we have it. This is the graph for the current and voltage relationship of the capacitor. And here is the voltage and current relationship in an inductor. As we've already explained in an inductor, the voltage, it is at its maximum when we first close a circuit, but eventually goes down to nothing. The current, because the voltage was pushing back, there was no current going through. But eventually, as the voltage gives up, it's allowing the current to flow. Therefore, the current is at maximum. I have stored its maximum current as an energy. Okay, capacitor is the opposite. Okay, when you first close a circuit, then the current was rushing in to charge it, correct? But eventually, as the parking lot or the bucket filled, the current rate was slowing down, but then the charge, the energy, was building up, just like the water in the water bucket or the parking lot with a lot of cars. Okay, so we've talked about how the current was leading the voltage, and we give a name for ICE, for current. Current is in front of the voltage or leading voltage, or voltage is lagging behind the current. But for this, we have voltage that is leading the current. Okay, for inductor, voltage is leading the current. So we have the name Eli, the Iceman, as a short way to remember that which one's leading and which one's lagging. Okay? One more thing that I want to talk about regarding this, guys, is that it is an important concept to remember and understand going forward to AC. Let's take a look at for capacitor. When the circuit is first closed, the current's at its maximum there is no voltage. What condition creates that? When we're just talking about resistors in a series or parallel circuit, what condition does it create that? Well, a short circuit will have a maximum amount of current, correct? And eventually goes down. When it's fully charged after 5 time constant, there is no current. If there is no current, what condition do we have in a circuit? It's like open. Remember we talked about in the capacitor, when it's fully charged, that light bulb will go out. Why? Because there's no current. Essentially, the capacitor opened the circuit. Okay? So this is important to know. When circuit is closed at first, capacitor behaves like short. On the other hand, when capacitor is fully charged, capacitor acts like open. Okay, let's take a look at for inductors. When we first close a circuit, when it starts to charge, do we have any current? No. When we don't have any current, what do we have? It's an open circuit. However, when it's fully charged, think about the water wheel, guys, right? It's flowing on its own. You don't need another push, right? It's like a short circuit. There's a maximum amount of current that's flowing. So let's write it down. When circuit is closed first. So for charging, inductor behaves like open. When inductor is fully charged, it behaves like short. Okay? Again, in DC, once it charges, that's it. It will forever, until you open it again, it will forever act like short. Imagine like the water wheel and the water pump, if I never turn the pump off, it's not the pump actually pumping the water anymore. It will be the momentum of the water wheel just kind of drawing the water in because of its momentum, correct? Until I turn it off, then it's going to do something different. And same thing for capacitor. If you close the circuit and leave it closed, it's charged, it will forever act like open. That light will never turn on until you open the circuit again. Then it's going to release the charge, therefore the light will come on and go off. However, for AC, because we have the alternating side, and these become very, very interesting and different. I want to talk about the inductive kickback, and that is a form of back voltage, but a bit more dangerous. Let's see how that happens. Here is a circuit with simple inductor and a power supply with switch. As soon as you close the switch, the flow is going to happen, and inductor is going to, as it's creating the magnetic field, it's going to oppose with the same amount of pressure that this was giving. If there was 5 volts of pressure that it was pressing, then it is going to instantly create 5 volts and push back, and it's going to slowly build up the magnetic field. When there is no more change of a current, before it was 0 current, because the circuit was open. As soon as I close the circuit, current was flowing, right? The current, it's not going to be all of a sudden 10. It's going to be increasing. As it was increasing, the rate was changing. The magnetic field was also growing. As it's growing, it's storing the energy, okay, ready to be sent. After 5 time constant, it finally stored all the energy in current, and it's happy the current is still flowing, and it's good to go. However, as soon as I opened the circuit, what is going to happen to this inductor? The magnetic field, because it opened almost instantaneously, there is no current. When there is no current, what happens to the magnetic field? It collapses almost immediately. When the current collapses immediately, all that energy, that, because we're talking about the rate of change, the rate is so soon, so immediate, so spontaneous, that rate of change creates a huge amount of voltage, which can be easily in hundreds of volts, or even sometimes thousands of volts, okay? And that amount of pressure is looking or sending the current to somewhere. And typically, when that force is being pushed, and it will send the way that the current was initially flowing. It was flowing this way. So I said, why are you stopping? Continue to flow. So it's going to send a current in this direction with hundreds or even thousands of voltage or even pressure. When that happens, you're going to arc, because the energy is such great. It's so much energy. Even though the circuit is open, it's going to try to jump the switch. Okay? That phenomenon is called inductive kickback. And it's nothing more than a back voltage. It is a back voltage. Inductive kickback is a back voltage, however, in much greater quantity of magnitude. And it is typically bad, and because it can damage the switch, it can damage other electronic components, because I've only drawn an inductor and switch and battery, but then, in a real life, you'll have other components like transistors and any other stuff like that. It's going to damage that, and it can even damage the power supply. So to prevent this inductive kickback, we have 2 ways to mitigate it. Okay, instead of having a regular inductor and a switch, we have what's called diode. And I haven't talked about diode so far, but diode is a one-way check valve for electricity, which means it only allows current to flow in one direction. Okay? And this line represents the cathode, and that arrow represents the anode, and it typically points the direction that the current should flow. So if you look at this diode here, okay, which way is the current flowing? It's going from positive to negative, and it goes down to, this is in parallel, right? And when you see this, the diode says, stop, you can't go this way. It's only one way. You can only go up, not up to down. You cannot do that. So like the current sees it, okay, fine, no problem, and then go through the inductor, which is good. But as soon as the switch is open, that energy that just created the hundreds and thousands of voltage are looking for somewhere to go. So instead of going towards the switch, because switch is still open, it needs to have a lot of energy to jump. Okay? What it does is like, oh, here's another path. Oh, can I go? Yes, I can, because it's pushing the current or voltage down in this same direction that the current was originally flowing, correct? So instead of pushing it through the switch, it's like, oh, I have another path, and I can go this way. That's what happens, positive to negative. Lovely, and I'll go, and then it just circles it around, it loops it around, thousand times, and that happens very, very quickly in about milliseconds. And it requires, we'll talk about the diode in the later lessons, it requires 0.7 volts approximately every time the current passes. Okay? It's like a gatekeeper. You need to pay me 0.7 volts. Okay, it will cost you 0.7 volts. So whatever the voltage that it was generated, let's say 500 volts, okay, that it was generated, it's going to loop around till it dissipates to 0. And how does it do that? Well, they have to pay the toll. Okay, this is the fee, 0.7. Every time it loops around, you have to pay. It's still better than jumping the switch. So we use diode for preventing an inductive kickback. Number 2 is the neon bulb. A neon bulb in schematic looks like this. Okay, what it is it's a bulb, but it's got some gases inside, and you will need a significant amount of voltage to have this light turned on. Okay, typically these neon bulbs operate around 70 to 90 volts. Now, that's high. Any regular battery or power supply won't be able to supply that kind of voltage. So in general, when it's connected in a regular circuit, let's say I place this instead of the diode. Kind of looks like a capacitor, isn't it? But anyways, this is a neon bulb. It acts like open because I need to have 70 volts. I need to see at least 70 volts to turn my light on. But if this is 10 volts, I don't have enough. So if you go, it's like, oh, that's too high. I can't go. All right, my level's too low. I have to go through the inductor. However, as soon as the switch opens, the inductive kickback, the back voltage been generated is, like I said, hundreds and thousands of volts, which is enough to turn this light on, the neon bulb, because it's more than 70 to 90 volts, right? So instead of going through the switch, it goes through that neon bulb. What that does is it reacts, it gives you a visual indication of flash, and then goes away, and that's how the energy dissipates. So there are two methods to mitigate the inductive kickback. Okay, it's not always that bad. Sometimes we use this in an advantageous way. A typical example is our spark plug. Okay, but when you're building a circuit without that kind of a purpose, you would always want to protect your circuit from inductive kickback by installing diode or neon bulb parallel to our inductor. And sometimes to even help the process, sometimes you put a little bit of resistor in there as well, small resistor as well. That way it's going to dissipate the energy a lot faster. All right, so now that we talked about the inductive kickback, let's see, remember how we talked about by adding capacitors in series and parallel? Let's see what happens with inductors. Okay, so let's see what happens if we add the inductors in series and parallel. Okay, we have L1, L2, and L3. And what do you guys think? Is my total inductance going to increase or decrease? In this case, it is going to increase. It will be equivalent to having a more cross-sectional area of an inductor. Okay, so we have very, very tightly packed inductors close together, and we have more cross-sectional area of the inductor. Therefore, the total inductance is going to increase. So in series, my LT is going to be L1 plus L2 plus L3. This is much better, right? And in parallel, and it's going to do the opposite. My inductance is going to decrease. Okay? So because my current is dividing, when I have a smaller current that's going through, while I have the less rate because my current is not going from 0 to, let's say, I don't know, 10 milliamps. Instead, it's going from 0 to 2 milliamps. That rate is very, very small. Okay, that the change from 0 to 2 milliamps is very small. Therefore, it's not going to have that much effect in the magnetic field. Therefore, it's going to reduce, or it's going to diminish my inductance total. And that formula is your favorite this one. Okay, so that is it for an inductor's theory for DC. We will talk about the AC theories in the next lesson. So hope you guys enjoyed it. I will see you guys in the next lesson. Thank you.